In the dim hush, before the first fires of civilization had been kindled, long before ink pressed against papyrus or bronze chisels carved the memory of kings into stone, humanity lifted its eyes to the sky and saw a darkness stitched with embers. Those distant sparks, scattered across the velvet canvas of night, seemed to pulse with secrets older than any story spoken around a fire. And so, in lands divided by deserts, rivers, and mountains, the earliest dreamers began tracing lines between those lights, naming patterns, inventing mythologies, and quietly marking the slow, deliberate clockwork of the heavens. Their imaginations, untethered by the limits of their world, stretched across the cosmic ocean, stirring the first questions whose echoes would ripple forward for tens of thousands of years. Questions of origin, motion, meaning, and destiny. Questions carved not in stone, but into the very trajectory of human curiosity. When the ancient Sumerians gazed at the glittering belt of the Milky Way, they described it as the path trodden by the gods. The Egyptians, attuned to the cycles of the Nile, watched Sirius, the dog star, rise just before dawn to herald the flooding of the river, believing it to be the soul of the goddess Supdet, shimmering back at them from the celestial canopy. And high in the Andes, long before the rise of the Inca Empire, the Quechua people did not merely see constellations formed by stars, but dark constellations, silhouettes shaped from the black clouds of interstellar dust blocking the starlight behind them. Their astronomers traced cosmic llamas, serpents, and foxes, not from the luminescent points, but from the voids between them, perceiving a universe textured not by light alone, but by its intricate shadows. As centuries accumulated along with the roots of time, the great civilizations of antiquity pressed deeper into the mysteries overhead. In Babylon, astronomer priests climbed ziggurats with clay tablets in hand, recording the wandering of planets with a precision that remains astonishing even now. They measured the sky not with telescopes, but with patience, the patient repetition of nightly observation, the patient recording of celestial alignments, the patient search for patterns hidden within the cosmic drift. Their archives, hardened by millennia of sun and desert, still bear the etched impressions of Jupiter's 12-year cycle and Venus's meticulous five-fold dance, inscribing the earliest fingerprints of scientific astronomy. Yet while the Babylonians calculated, the Greeks questioned. They did not settle for tracking the movements of celestial bodies. They demanded to know the architecture behind those movements. In the bustling agora of ancient Athens, philosophers argued beneath the open sky, gesturing toward constellations like actors on a stage suspended above them. Thales sought order in the heavens, proposing that celestial phenomena obeyed natural laws rather than the whims of gods. Anaximander envisioned Earth floating unsupported in space, a radical break from the ancient belief that the world rested on pillars, turtles, or divine shoulders. Then came Pythagoras, whose followers whispered that the cosmos was not mere chaos, but a symphony of mathematical harmony. its planets moving in silent, invisible music. But it was Aristotle who would cast the longest early shadow, sketching a universe of perfect spheres nested like the layers of an onion, each moving with crystalline regularity. For him, the heavens were immutable, flawless, eternal, and utterly separate from the ever-changing world below. And for nearly 2 millennia, that image, Earth at the center, celestial objects affixed to perfect spheres, would dominate the imagination of scholars, shaping the way medieval Europe, Islamic astronomers, and Byzantine thinkers envisioned the cosmos. Yet, even during the centuries in which Aristotle's geocentric world seemed unshakable, voices across continents probed the heavens with different methods and reached profoundly different conclusions. In India, mathematicians of the Gupta Empire derived models predicting planetary motions with an elegance that would later astonish European scholars. In the great observatories of the Islamic Golden Age, from Baghdad's House of Wisdom to the lofty instruments of Samarkand, astronomers refined star catalogues, measured eclipses, and developed trigonometric tools that would empower later generations to finally pierce the errors of ancient cosmology. Al-Biruni calculated Earth's radius with a precision that modern scientists would not surpass for centuries. Al-Battani refined the length of the solar year, and Ibn al-Shatir constructed a model of the planetary system so accurate that Copernicus's diagrams would echo its geometry more than 100 years later. By the time Nicholas Copernicus, working under the quiet candlelight of a Polish cathedral tower, dared to propose that Earth itself revolved around the sun, the idea was not as sudden or heretical as legend often suggests. Instead, it was the next step in a chain of revelations extending back through Damascus, Baghdad, Alexandria, and Babylon. Copernicus, drawing from ancient Greek manuscripts and Arabic astronomical tables, placed the sun at the center of a dynamic, heliocentric system. It was a bold inversion, yet delivered with almost whisper-like caution, a whisper that would soon thunder across Europe as telescopes brought the heavens into sharper focus than any human eye had ever achieved. When Galileo Galilei tilted his handmade telescope toward Jupiter on a crisp January night in 1610, he found 4 tiny stars moving night after night, not around Earth, but around Jupiter, a miniature solar system orbiting another world. Their dance shattered the ancient certainty that all celestial bodies circled our planet, revealing instead a universe of intricate relationships. Soon after, Galileo detected mountains and craters on the moon, proving that the heavens were not flawless. He observed the phases of Venus, confirming Copernicus's heliocentric model, and he traced sunspots across the solar surface, demonstrating that even the sun was neither eternal nor unchanging. Each discovery dissolved a pillar of the old celestial order, replacing it with a universe more dynamic and unpredictable than philosophers had dared imagine. While Galileo confronted the skies with lenses Johannes Kepler confronted them with mathematics. Kepler inherited the meticulous observations of Tycho Brahe, who for decades had recorded planetary positions with unmatched precision. But the data refused to align with the perfect circles demanded by tradition. Kepler, wrestling with both numbers and faith, realized that celestial bodies did not trace divine circles, but ellipses, oval paths dictated by geometric necessity rather than aesthetic perfection. His three laws of planetary motion transformed the solar system from a clockwork into a mathematical engine, opening the door to Isaac Newton, who would reveal the invisible force binding the cosmos together. Newton's law of universal gravitation, simple enough to write in a single line, profound enough to describe the motions of planets, falling apples, comets, and tides, united the heavens and earth in a single physical framework for the first time in history. With his equations, the cosmos was no longer a distant, mystical realm, but a grand laboratory governed by intelligible laws. Telescopes grew larger, observatories multiplied, and astronomers charted nebulae, star clusters, and swirling smudges of light whose nature remained mysterious but tantalizing. By the 18th century, explorers of the sky began cataloging these faint celestial clouds, suspecting that some were vast systems of stars, island universes, as Immanuel Kant called them. William Herschel, constructing telescopes from molten metal in his backyard workshop, discovered the planet Uranus, mapped binary stars, and attempted to sketch the shape of the Milky Way using star counts like a surveyor measuring invisible terrain. His sister Caroline Herschel discovered comets and nebulae, her work expanding the edges of the known cosmos while quietly rewriting the history of women in science. As the Industrial Revolution reshaped Earth, a new revolution unfolded in the night sky. Photography, that strange fusion of chemistry and light, allowed the heavens to leave their own fingerprints in silver grains. Nebulae resolved into spirals. Star clusters glittered like frozen fireworks. And in 1924, observing the faint pulsing of a star called a Cepheid variable in the Andromeda Nebula, Edwin Hubble calculated that this smudge was not a part of the Milky Way at all, but a separate galaxy, one far beyond the borders of our own. Its light stretched across 2.5 million years of time. That discovery detonated the size of the universe. The Milky Way, once thought to encompass all creation, became one galaxy among billions. And the universe itself, far from static, began to look more like a vast, expanding fabric, a concept confirmed when Hubble found that distant galaxies were racing away from us, their light reddened by the stretching of space itself. An expanding universe implied a beginning, a moment when all matter, energy, space, and even time itself were compressed into an unimaginably dense seed. Yet in the early 20th century, the notion of a cosmic birth was met with skepticism, even ridicule, as many scientists preferred the comfort of an eternal, unchanging cosmos. But Belgian priest and physicist Georges Lemaitre, drawing upon Einstein's equations with quiet conviction, proposed that the universe had begun as a primeval atom, a cosmic egg from which all creation burst. His idea seemed philosophically charged, even theologically suspicious to some, but the mathematics supported it, and the evidence would soon accumulate like fossils embedded in the bedrock of time.
In 1965, two radio engineers, Arnaud Penzias and Robert Wilson, attempted to remove a persistent hiss from the antenna of a communication experiment in New Jersey. They cleaned the instrument, chased off nesting pigeons, inspected wiring, and recalibrated electronics, but the background noise persisted, uniform, faint, and omnipresent. Only later did they realize that they had stumbled upon the afterglow of the Big Bang itself, a ghostly whisper of microwave radiation left over from a time when the universe was only 380,000 years old. This relict light, mapping the earliest texture of the cosmos, revealed tiny temperature fluctuations, seeds from which galaxies, star clusters, and galaxy superstructures would eventually form. As the 20th century advanced, astronomers refined their instruments and expanded the cosmic timeline. Radio telescopes caught signals from pulsars, neutron stars spinning with machine-like regularity, their beams sweeping across space like cosmic lighthouses. Quasars, once thought to be stars, revealed themselves as the blazing hearts of ancient galaxies, powered by supermassive black holes devouring matter with insatiable hunger. Spectrographs, measuring the chemical fingerprints of starlight, uncovered the abundance of hydrogen, helium, and trace elements forged in the early universe and in the fiery furnaces of dying stars. Meanwhile, humankind's restless ambition shifted skyward in more literal form. Rockets, once imagined only in mythology or speculative fiction, hurled machines and explorers beyond the cradle of Earth. When Voyager 1 and 2 departed the solar system in the late 1970s, their golden records carried human music, greetings, and images, tiny emissaries of our species riding on spacecraft no larger than compact cars, destined to wander the interstellar gulf for millions, perhaps billions of years. Yet even as these machines ventured outward, telescopes such as Hubble peered deeper inward, revealing structures so immense they defied language. The pillars of creation, towering columns of gas in the Eagle Nebula, stood like cosmic cathedrals sculpted by starlight. Gravitational lensing bent light from galaxies behind massive foreground clusters, proving that unseen matter, dark matter, permeated the cosmos like an invisible scaffold. Dark matter itself revealed no glow, no heat, no interaction with normal atoms except through gravity. Vera Rubin, observing the rotation curves of galaxies, found that stars near the edges orbited as swiftly as those near the center, defying Newtonian expectations unless a huge unseen mass enveloped each galaxy like a shadowy halo. Her careful, persistent work transformed dark matter from speculative curiosity into an unavoidable physical reality. And yet, despite decades of searching, its true nature remains hidden, an enigma lodged at the heart of modern cosmology. If dark matter challenged the known, dark energy deepened the mystery. In the late 1990s, two teams of astronomers studying distant supernovae discovered something astonishing. Not only was the universe expanding, it was expanding faster over time. Some unknown force was accelerating the cosmic expansion, stretching space itself with growing intensity. This force, dubbed dark energy, now dominates the universe, dictating its long-term fate with calm but inexorable power. Whether it will continue indefinitely, fade away, or ultimately reverse remains an open question, one whose answer may shape the destiny of every star and galaxy in existence.
Yet, as astronomers probed the largest cosmic scales, they also uncovered the intricate histories of stars, those nuclear beacons scattered across the firmament. Each star is a self-contained saga, beginning with clouds of hydrogen collapsing under gravity until their cores burn with fusion. Some burn slowly and live for tens of billions of years. Others blaze intensely and vanish quickly in supernova explosions that scatter heavy elements into space. These explosions seed future star systems with the ingredients of planets, oceans, atmospheres, and life itself. The iron in human blood, the calcium in bones, the carbon in every leaf, all were forged in the throats of ancient stars that died long before Earth was born. Among the many stellar species, none are more extreme than neutron stars and black holes. Neutron stars compress a sun's worth of mass into a sphere barely 20 kilometers across. Their surface is so dense that a sugar cube of their material would outweigh Everest. Their magnetic fields whip particles around at near light speed, creating beams that flash like cosmic strobe lights. Black holes, born from collapsing massive stars or from the dense centers of young galaxies, exert gravitational influence so strong that not even light can escape. At their event horizons, time slows, space distorts, and the familiar laws of physics crumble into a mysterious singularity where our understanding falters. But black holes are not merely engines of destruction. They shape galaxies, regulate star formation, and influence cosmic evolution. Seen from afar, the regions around them glow brighter than entire galaxies, fueled by spiraling disks of superheated matter. When two black holes collide, they send ripples through space-time, gravitational waves predicted by Einstein, but only detected a century later by the LIGO observatory. These waves, passing through Earth as faint tremors in the fabric of reality, confirmed yet another piece of the cosmic puzzle and opened a new form of astronomy capable of hearing the universe as well as seeing it. While astronomers mapped the violent and the vast, planetary scientists turned their attention to worlds closer to home and to those scattered across distant star systems. The first confirmed exoplanets, discovered in the 1990s, were unexpected: massive gas giants orbiting close to their stars, roasting in infernal heat. But as detection techniques improved, an entire menagerie emerged: water worlds, lava planets, frozen giants, and rocky spheres orbiting in habitable zones where liquid water might persist. Kepler's Space Telescope revealed that planets are ubiquitous, likely numbering in the hundreds of billions within the Milky Way alone. Some of these planets orbit stars far smaller and dimmer than the Sun, such as the TRAPPIST-1 system, where 7 Earth-sized worlds trace tight, resonant orbits, each one close enough to the next that a person standing on one planet could see others looming large in the sky like neighboring moons. Other systems harbor super-Earths, rocky worlds larger than our own, with stronger gravity, thicker atmospheres, and perhaps oceans stretching across global basins. Still others orbit binary stars, living under dual sunsets, reminiscent of ancient myths and modern fiction alike. The more the universe revealed itself, the more it challenged human assumptions about the uniqueness of Earth. Biological precursors, organic molecules, amino acids, and complex carbon structures appeared in meteorites, comets, and interstellar clouds. Spectrographs detected water vapor in the atmospheres of exoplanets, methane in the plumes of Saturn's moon Enceladus, and carbon-based chemistry on Titan beneath its golden haze. Everywhere scientists looked, the building blocks of life appeared not as rare anomalies, but as recurring motifs woven into the cosmic tapestry. Meanwhile, computer simulations grew more sophisticated, tracing the evolution of galaxies from the earliest epochs of cosmic history. These simulations revealed that galaxies formed within dark matter halos, merging and colliding in a gravitational ballet spanning billions of years. Spiral galaxies wound their arms through rotating disks. Elliptical galaxies formed from ancient collisions. Dwarf galaxies clustered like satellites around giants. The structure of the universe itself resembled a cosmic web, vast filaments of galaxies stretching across mind-bending distances, separated by enormous voids where little matter resides. Superclusters knotted together like luminous pearls along these filaments, while streams of gas and dark matter fed galaxies like arteries sustaining a living organism. Yet amid all these discoveries, one question loomed over every observation, calculation, and theory: how much of the universe could we ever hope to know? The observable universe is limited by the speed of light and by the finite age of cosmic time. Beyond the horizon of what we can observe lies a realm forever inaccessible to telescopes or signals, expanding faster than information can travel. In that frontier of perpetual mystery, galaxies drift into unreachable distance, and the cosmic web stretches into darkness we neither map nor imagine fully. The universe likely extends far beyond what humanity will ever see, perhaps infinitely, perhaps folding into shapes beyond our mathematics, perhaps splintered into multiple regions with different physical laws. Yet even this limit, the cosmic horizon, became a subject of inquiry, for astronomers and physicists began to suspect that the visible universe was only a tiny shimmering island in a vastly larger sea. Some theories proposed that the universe underwent a brief but extraordinary burst of inflation in its earliest fraction of a second, expanding faster than the speed of light, not because objects exceeded cosmic speed limits, but because space itself ballooned outward in a breathtakingly rapid metamorphosis. This inflation would have stretched primordial fluctuations into the seeds of galaxy formation and created regions of space forever unreachable from our own. Other theories ventured even further into speculation, imagining a multiverse composed of countless bubble universes, each with its own laws of physics, popping into existence like ephemeral blooms on the cosmic ocean. While such ideas stirred both wonder and controversy, astronomers continued to refine their understanding of the universe's earliest moments. Particle accelerators probed the conditions of the first microseconds after the Big Bang, recreating tiny bursts of primordial plasma where quarks and gluons danced freely before condensing into protons and neutrons. Observatories measured the cosmic microwave background with exquisite precision, revealing a universe far from uniform, one textured by slight clumping that foretold the later formation of galaxies. Simulations traced how dark matter condensed into halos, drawing luminous matter with it, guiding the grand architecture of the cosmos like invisible hands shaping clay. But even as scientists dissected the early universe, they also turned to some of its strangest inhabitants, objects that defied the simplicity of traditional celestial classification. Among them were rogue planets, worlds untethered to any star, wandering through interstellar darkness like nomads. These cold, lonely spheres might outnumber stars themselves, forged in turbulent planetary nurseries, only to be ejected by gravitational skirmishes. Some drifted with thin atmospheres, warmed only by internal heat. Others carried moons trailing silently behind them, their surfaces illuminated only by distant starlight or the faint glow of cosmic background radiation. At the opposite end of strangeness lay hypervelocity stars, stellar cannonballs flung across galaxies by gravitational interactions with supermassive black holes. These stars soared through interstellar space at millions of kilometers per hour, their trajectories tracing dramatic arcs like arrows shot from ancient war bows. Some were destined to escape the Milky Way entirely, carrying with them chemical signatures from the regions of their birth, becoming stellar ambassadors to the intergalactic void. Meanwhile, astronomers studying the hearts of galaxies discovered structures so vast and energetic they seemed almost alive. Active galactic nuclei spewed jets of particles stretching thousands of light years, their beams carving through cosmic gas like colossal laser lances. Radio lobes inflated behind them like twin balloons, sculpting the surrounding medium. These energetic eruptions influenced star formation for millions of years, sometimes quenching it, sometimes triggering new bursts of birth within dusty regions. The universe, it appeared, was not a static collection of stars, but a complex ecological system, a vast interplay of creation, destruction, and transformation. As telescopes improved, new mysteries emerged, including one that would confound physicists for decades: the strange acceleration of spacecraft as they ventured into the outer solar system. The Pioneer anomaly, a subtle deviation from expected trajectories, sparked debates about modified gravity, thermal radiation, and even exotic physics. Though eventually explained through detailed engineering analysis, the anomaly highlighted the delicate interplay between science and mystery, reminding researchers that even familiar territories hold secrets waiting to be uncovered.
Meanwhile, gamma-ray bursts, brief but extraordinarily energetic events, flashed across distant galaxies, outshining entire cosmic systems for mere seconds. These bursts, detected by orbiting satellites, were initially so intense that some scientists wondered whether they heralded catastrophic events within our own galaxy. But as observations accumulated, a clearer picture emerged. Gamma-ray bursts signaled the collapse of massive stars or the merging of neutron stars, releasing colossal amounts of energy and forging heavy elements such as gold and platinum in the process. The jewelry adorning human civilization was thus traced back to cataclysmic events occurring billions of years before humanity evolved the capacity to appreciate their luster. Yet for all its violence, the cosmos also harbored serene and graceful structures. Rings of Saturn sculpted by icy moons, spirals of galaxies winding like ancient calligraphy, planetary nebulae expanding in delicate patterns as dying stars exhaled their outer layers. The Helix Nebula resembled the colossal cosmic eye. The Cat's Paw Nebula teemed with stellar nurseries. The Ant Nebula displayed symmetrical lobes shaped by unknown forces. Some structures looked so eerily geometric, like the hexagonal storm on Saturn's North Pole, that they defied intuitive explanation, inviting deeper research into atmospheric dynamics and planetary magnetism. Cosmic magnetism itself became a subject of renewed fascination. Invisible, pervasive, and immensely influential, magnetic fields shaped the behavior of plasma, guided cosmic rays, and influenced the structure of interstellar clouds. They wrapped galaxies in vast halos,
threaded filaments of the cosmic web and twisted around black holes in intricate spirals. Understanding these magnetic architectures required the combined expertise of astrophysics, fluid dynamics, and computational modeling, each shedding light on a different facet of the magnetic tapestry woven across the universe. Meanwhile, time itself, once thought absolute, proved to be another fragile assumption. Einstein's theories revealed that gravity warped time, slowing its passage near massive bodies. This meant that clocks on Earth's surface ticked differently than those in orbit. Astronauts aged ever so slightly slower than those they left behind. Time dilation became not merely a theoretical abstraction, but a measurable reality, influencing GPS satellites and shaping our understanding of cosmic evolution. Light from distant galaxies, stretched by the expansion of space, carried with it information about ancient epochs, enabling astronomers to peer back billions of years with each observation. As the universe revealed itself across greater spans of time and space, humanity's technological reach grew in tandem. The James Webb Telescope, with its vast golden mirror unfolding like a celestial flower, captured light from the first generations of stars, objects so distant their photons had been traveling since the infancy of the cosmos. Webb's infrared gaze penetrated dust clouds, revealing the hidden nurseries where stars ignited into being. It traced the chemistry of exoplanet atmospheres, detected carbon-bearing molecules in distant systems, and offered glimpses of galaxies whose structures hinted at processes still poorly understood.
But the cosmos did not wait for human understanding. It continued its ceaseless evolution. Stars aged, galaxies collided, and cosmic structures shifted with the slow, deliberate rhythm of eons. Meanwhile, the solar system, once considered stable and unchanging, revealed its own dynamic complexity. Asteroids drifted through belts sculpted by Jupiter's gravity. Comets carried icy relics from the solar system's earliest eras. Kuiper Belt objects orbited in resonances that hinted at past migrations of the giant planets. The discovery of countless dwarf planets, including Eris, Haumea, and Makemake, challenged the traditional view of planetary classification, revealing a rich diversity of bodies beyond Neptune. And far beyond the Kuiper Belt, the Oort cloud, an immense spherical reservoir of comets, stretched toward the interstellar medium like a distant frontier. Though unobserved directly, its existence was inferred from the trajectories of long-period comets whose orbits suggested origins far beyond the familiar planetary realm. The Oort cloud represented the solar system's deep memory, a frozen archive of material unchanged since the dawn of the sun itself. As researchers studied the cold outskirts of the solar system, they also turned inward, examining the sun with unprecedented precision. Helioseismology, the study of solar oscillations, revealed internal layers and rotation patterns. Satellites monitored solar flares and coronal mass ejections. Neutrino detectors captured ghostly particles produced in the sun's core, confirming theories of nuclear fusion. The sun, once regarded as a static lamp in the sky, emerged as a complex and dynamic star, its magnetic cycles influencing everything from auroras to power grids. Meanwhile, planets such as Mars, Venus, and Jupiter became subjects of intensive exploration. Rovers crawled across Martian plains, analyzing sediments and capturing panoramic vistas of ancient riverbeds. Landers descended through Titan's orange haze, splashing into methane lakes. Probes plunged into Jupiter's atmosphere, measuring its swirling storms and enigmatic core. Each mission revealed truths stranger than fiction. Venus's crushing pressures and sulfuric clouds, Jupiter's metallic hydrogen depths, and Mars's seasonal methane plumes, hinting at possible biological or geological origins. Yet, as humanity explored its local cosmic neighborhood, the universe remained vast beyond comprehension. The cosmic web stretched across distances so immense that light, traveling at 300,000 kilometers per second, would require billions of years to cross from one end to another. Superclusters rotated with ponderous grace. Voids expanded like dark caverns, and at the largest scales, the universe appeared both chaotic and ordered, turbulent and serene, ancient and perpetually young. At these colossal scales, gravity, so gentle that a magnet can lift a paperclip against Earth's pull, became the grand sculptor of cosmic architecture. Over billions of years, it coaxed matter into vast filaments, drew galaxies into clusters, and directed the slow dance of mergers that shaped their evolution. When galaxies collided, their stars usually passed by each other unharmed, separated by immense distances. But their gas clouds clashed violently, triggering waves of star formation that illuminated the aftermath like cosmic fireworks. In some mergers, supermassive black holes spiraled together at their centers, warping space-time with gravitational waves that would eventually be detectable across hundreds of millions of light-years. These colossal unions shaped the fate of galaxies, determining whether they evolved into spirals with elegant arms or into dense ellipticals filled with ancient red stars.
Even within galaxies, cosmic events unfolded across scales both subtle and dramatic. Star formation proceeded in cold molecular clouds where temperatures dropped so low that hydrogen molecules clustered like dew forming on morning grass. These clouds, shielded from the glare of nearby stars, collapsed into clumps that ignited when their densities reached critical thresholds. Jets burst from newborn stars, carving cavities in surrounding gas. Dust grains coalesced into pebbles, pebbles into boulders, and boulders into planetesimals, the precursors of planetary systems. Observations of young stellar objects revealed swirling disks, punctuated by dark rings where planets had begun carving pathways through the material, offering snapshots of the earliest stages of planetary genesis. Meanwhile, the interstellar medium, the vast, tenuous gas permeating galaxies, served as both the graveyard of dying stars and the womb of new ones. Supernova explosions sent shockwaves through this medium, compressing gas in some regions while dispersing it in others. Cosmic rays, accelerated by magnetic fields and stellar remnants, streamed through space and interacted with interstellar atoms, creating exotic molecules that drifted through the cold expanse. Among these molecules were complex organic compounds, alcohols, hydrocarbons, and even precursors to amino acids, revealing that chemistry essential for life was not confined to planets, but spread across nebulae like seeds scattered by an unseen gardener. Over time, astronomers realized that understanding the cosmos required blending observations from every possible wavelength. Radio telescopes captured whispers from hydrogen clouds. Infrared observatories traced the heat of newly forming stars. Optical telescopes revealed the light of mature galaxies. Ultraviolet instruments recorded the glow of hot, young stars. X-ray and gamma-ray detectors exposed the violent, high-energy processes at the edges of black holes or in the hearts of supernovae. No single view could provide the full narrative. Only a synthesis of all wavelengths, each revealing a different chapter, allowed the cosmic story to unfold in its full complexity. But even with this multi-wavelength approach, new mysteries emerged. One of the most perplexing was the discovery of fast radio bursts, brief, intense flashes of radio waves lasting mere milliseconds, yet releasing more energy than the sun emits in days. These bursts, originating from distant galaxies, appeared sporadically and unpredictably, eluding easy explanation. Some repeated, some did not. Some followed patterns, others seemed completely random. Theories ranged from magnetars undergoing starquakes to interactions in turbulent plasma near black holes. Each hypothesis illuminated a new facet of cosmic possibility. Alongside these enigmatic bursts came the study of cosmic voids, immense regions where galaxies were scarce and matter density was astonishingly low. These voids, spanning tens or even hundreds of millions of light-years, formed the negative space of the cosmic web. They were not empty, but sparse, containing faint dwarf galaxies, diffuse gas, and the subtle gravitational tugs of dark matter. Studying voids became a way to test cosmological theories, for the behavior of matter in these regions revealed clues about dark energy, the expansion of space, and the geometry of the universe. Yet, for all the enormity of cosmic structures, some of the most intriguing discoveries lay in the physics of the very small. Quantum mechanics, governing the realm of particles and fields, proved essential to understanding the early universe and the behavior of exotic objects like neutron stars. Quantum fluctuations during inflation might have seeded the cosmic structures observed today. virtual particles flickered into and out of existence, contributing to vacuum energy, a possible link to dark energy itself. In neutron stars, quantum degeneracy pressure prevented collapse, while in black holes, quantum effects predicted the slow evaporation of their mass through Hawking radiation, a process so faint it has never been observed directly, but remains one of the most profound theoretical insights in modern physics. Meanwhile, the search for extraterrestrial life progressed in step with the study of astrophysics. Radio arrays scanned the sky for signals from distant civilizations, while optical surveys searched for unusual light patterns that might indicate engineered structures. The concept of technosignatures, detectable signs of advanced societies, expanded beyond radio waves to include megastructures, unusual infrared emissions, and even anomalies in the timing of pulsars. Although no confirmed signs of intelligent life emerged, the search itself expanded human understanding of the possibilities woven throughout the cosmos. At the same time, developments in astrobiology revealed that life's building blocks could form in a variety of environments. Hydrothermal vents on Earth's ocean floors demonstrated that life did not require sunlight, opening the possibility of ecosystems thriving beneath the icy crusts of moons like Europa and Enceladus. Titan's methane lakes suggested entirely different chemical pathways. Mars's ancient riverbeds and subsurface ice hinted at a past potentially rich in microbial life. These discoveries redefined the criteria for habitability, suggesting that life might flourish in places once dismissed as barren or hostile. Yet, as humanity pondered the emergence of life elsewhere, it also confronted the long-term fate of life in the universe. Stars like the Sun would eventually exhaust their nuclear fuel, expanding into red giants before shedding their outer layers to form planetary nebulae. More massive stars would die in supernovae, leaving behind black holes or neutron stars. Galaxies would continue merging, star formation would slow, and the universe itself, driven by dark energy, would drift toward a fate that depended on the true nature of this mysterious force. If dark energy remained constant, the cosmos would expand forever, growing increasingly cold and empty as stars burned out and black holes slowly evaporated. If dark energy changed over time, more exotic fates, such as a big rip, tearing cosmic structures apart, remained conceivable. Through all this, the human perspective remained both infinitesimal and extraordinary. From a tiny world orbiting an ordinary star on the outskirts of an unremarkable galaxy, humanity had glimpsed the birth of the universe, mapped its structure, decoded the life cycles of stars, uncovered planets orbiting distant suns, and measured the behavior of space-time itself. The cosmos, once perceived as a divine mystery reserved for gods and myth, had become a grand narrative woven through centuries of tireless observation, imaginative theory, and unwavering curiosity.
Still, the story pressed forward. New telescopes emerged with capabilities far beyond their predecessors. Extremely large telescopes with mirrors spanning dozens of meters, prepared to peer into the atmospheres of Earth-like exoplanets, searching for chemical signatures that might indicate biological processes. Gravitational wave observatories planned upgrades to detect mergers involving objects never observed before, perhaps black holes of intermediate mass, or collisions taking place in galaxies billions of light-years away. Space missions charted new courses to icy worlds, comets, asteroids, and the heliosphere's distant boundary, where the sun's influence waned and interstellar space began. And so the cosmic narrative continued its forward momentum, not as a closed tale, but as an ever-deepening exploration, an odyssey through time, matter, energy, and the enormous silence that lies between the stars. Yet even as the tools of exploration grew more sophisticated, the universe retained a talent for unveiling surprises that challenged long-held assumptions. One such revelation emerged from the study of galactic halos, vast regions surrounding galaxies where dark matter dominated and where the faintest stars drifted like ancient ghosts. These halos, once considered relatively quiet outskirts, proved far more dynamic. Streams of stars, remnants of smaller galaxies torn apart by tidal forces, wrapped around the Milky Way like ethereal ribbons. Each stream was a fossil of a long-consumed companion, a visible scar recording the galaxy's turbulent diet over billions of years. Such stellar archaeology revealed that galaxies were not static islands, but voracious organisms, endlessly absorbing smaller neighbors in a continuous cycle of growth and renewal. As these discoveries accumulated, simulations of galactic evolution became essential tools for deciphering the underlying mechanics. On vast supercomputers, billions of particles representing dark matter and baryonic matter interacted according to the laws of physics, evolving from the earliest instance after the Big Bang to the sprawling cosmic networks revealed by modern surveys. These simulations demonstrated how slight primordial perturbations, tiny imbalances in density, grew into clusters and filaments, setting the stage for the emergence of galaxies, stars, and planetary systems. The remarkable fidelity of these simulations allowed astronomers to test theories of dark matter, dark energy, and astrophysical feedback processes, refining their models in a continuous dialogue between computation and observation. But the simulations also highlighted how much remained unknown. Alternative theories of gravity vied with traditional dark matter explanations. Modified Newtonian dynamics attempted to account for galaxy rotation curves without invoking unseen mass. Exotic particles known as WIMPs or axions became leading candidates for dark matter, though none had yet been detected. Experiments buried deep underground or launched into orbit continued searching for faint interactions that might reveal dark matter's identity. Each null result sharpened the mystery, narrowing the field of possibilities while deepening the intrigue.
Yet the story of the cosmos was not solely one of matter. The behavior of energy, particularly radiation, played an equally critical role. Ultraviolet radiation from newborn stars carved cavities in surrounding gas clouds, influencing the rate of star formation. Ionizing photons from ancient population 3 stars, the first stars to ignite in the universe, reionized the intergalactic medium during a transformative era known as the Epoch of Reionization. Gamma-ray bursts, though rare, injected enormous energies into their surroundings, potentially influencing the habitability of nearby worlds. Even more subtle were the neutrinos, nearly massless particles streaming through the universe in imaginable numbers. Produced in nuclear reactions within stars, supernova explosions, and the early universe, these particles barely interacted with matter, passing through entire planets unhindered. Detectors buried deep within Earth captured only faint traces of their presence, yet these traces held clues about processes occurring in places otherwise unreachable, inside stellar cores, during supernova collapses, or in the first seconds of cosmic history. Over time, humanity's understanding of the cosmos grew not only from new data, but from the ability to interpret it through advancing mathematical frameworks. Techniques from statistical mechanics, fluid dynamics, general relativity, and quantum field theory intertwined to create a unified, though still incomplete, tapestry of cosmic behavior. The interplay of these disciplines mirrored the interconnectedness of the universe itself, where no phenomenon existed in isolation. Stars influenced galaxies, galaxies influenced cosmic expansion, expansion influenced the fate of space-time, space-time influenced the paths of particles, particles influenced the formation of atoms, molecules, and ultimately life. And through all this complexity, humanity continued refining its tools. Telescopes deployed to the far side of the moon were proposed to escape Earth's interference entirely. Interferometers combined light from widely separated observatories, achieving resolutions once unimaginable. CubeSats carried miniature observatories into orbit. Balloon-borne telescopes drifted above Earth's atmosphere, capturing ultraviolet light normally blocked by the planet's protective layers. Each innovation opened a new window onto phenomena previously hidden behind technological limitations. Still, the cosmos remained far larger than any set of instruments could encompass. Observatories detected structures spanning hundreds of millions of light years, walls of galaxies stacked like cosmic masonry, filaments bridging vast voids, and superclusters stretching across unimaginable distances. The Sloan Great Wall, the Hercules Corona Borealis Great Wall, and other immense structures pushed the boundaries of what cosmological theories predicted, questioning whether the universe was truly homogeneous on the largest scales, or whether previously unknown physical processes shaped these colossal formations.